Okay, so here's what we were talking about last time, how to do second derivatives with a chain rule. This is a classic first example. So the idea is we're going to suppose that we have z as a function of x and y, and that we also have x and y as functions of r and theta, if you're previously familiar with polar coordinates. And you see why we would do this. Otherwise, don't worry about it. We'll get to that later. Presuming that we understand the green derivatives and the blue derivatives, how do we go about taking, for example, the partial of that variable with respect to that variable? In other words, trying to view z as a function of r and theta in the composition, right? How do we compute those partial derivatives? Okay, so we talked about this part last time. There's z, there's r. Look at the two different paths. That first path gives us that term. This second path gives us that term. So that's the chain rule. Now, don't forget that specific knowledge like that, for example, allows you to actually compute some of these partials. If you happen to know exactly what x and y are as functions of r and theta, in this case we do, then go ahead. Right now, of course, we can't do any such thing here. I don't know what this f function is, so I basically can't rewrite this. I've made a different notational choice, but I didn't really actually make any mathematical progress there. Okay. All right. Where does the second derivative come in? What do you do in the case of that second derivative? We're going to, of course, take our r partial that we just computed, and we're going to take a partial of it. Right, there's no surprise there. The question is, how do you interpret stuff like this? What does it mean, if you're looking at something like zx, what does it mean to take an r partial of zx? How do you interpret that? Do you just write zxr? What a lot of students want to do. Let me just point out, saying zxr doesn't make any sense at all. Just a quick point here. If you were to write z, or zrx, take your pick. What would this mean? That suggests, first, that I'm going to view z as being a function of x and y, and then effectively as part of the same calculation, I want to then subsequently view z as a function of r and theta. So which is it? Right? Are we saying that z is a function of all of these? That doesn't make any sense at all. I can't momentarily view x as the variable and hold all of these constant. That doesn't make any sense. If r and theta are constant, so is x. The whole thing doesn't make any sense at all. Okay, so you can't do this. Please steer clear of that. What you have to do is realize that if z is an expression involving x's and y's, no surprise, if you take this expression involving x's and y's and take a partial with respect to x, this expression in terms of x's and y's is going to turn into another expression in terms of x's and y's. Right? So, this thing, zx, is on your diagram. You should explicitly note it as such. It is a function of x and y. Right? So I encourage you to explicitly put that down in your diagram like this. Again, I think it's really valuable to have this written down as explicitly on the page as a diagram, so that you can see how the arrows go, and therefore which paths you have to think about. Okay. All right. So with that supplemented on our diagram, let's then proceed. Again, this r partial that we've already computed. Right, if I want to compute the second partial with respect to r, I need to take the r partial of my existing r partial. Right? So we find ourselves looking at this. Let's look at this first term here, the r partial of that thing. Now, do keep in mind that we have a product rule deal here. So zx cosine theta. Notice that if you're taking the partial with respect to r, taking the partial with respect to r says you're holding theta constant. If theta is a constant, then cosine theta is a constant. What we have here is a constant times zx. The derivative of a constant times zx is, well, that constant just factors out. Right. Now, you won't always get that lucky. This is nice. Lucky break. We happen to get a product where one of the factors in the product was a constant. If this were not the case, no big deal. You just use the product rule. Separate, write that derivative of a product as a sum of two separate terms and proceed, right? It's not that big a deal. Just got lucky in this case. All right. So here's where it gets interesting. Oh, likewise, by the way, for over here, sine theta is a constant. Okay. Here's where it gets interesting, though. What do we do about this? Partial of zx with respect to r. And again, here's where you're going to find that temptation to just write zxr or partial zx or partial z with respect to x with respect to r or something like that, which again is really hard to make sense out of. But look at the diagram. There's zx. There's r. The diagram tells you exactly what to do. You have there a green path that gives you a term, and you have here a second path, let's color it in blue, and that gives you a term. X and y are intermediate variables there. And you get corresponding terms. Okay, so that's what that purple factor turns into. Don't forget, it is surprisingly easy when you're spending time worrying about how to apply the chain rule to a derivative term. It's surprisingly easy to kind of forget about that extra factor of cosine theta on the right, things like that. So do try to be notationally organized, right? Lay your work out on the page so that it's harder to forget, stuff like that. Anyway, there's that. But what I have highlighted in purple is the point here. That's the interesting part. That's where you're doing the real work on this problem. Okay. All right. Likewise, partial of zy with respect to r. There's zy. There's r. Path. Term. Path. Term. Right? Same deal. Okay. All right. And then it's all over with the shouting at this point. So a couple other freebies. Don't forget, we know how x is a function of r in this case. And don't forget this factor of cosine theta. Altogether, then, you get cosine squared theta. Okay. Stuff like that. Hey, what do we do with this? Partial of zx with respect to x. Is that a chain rule problem? Do I have to expand that out with a couple of terms or something? You're going to kind of wonder until you look at the diagram and realize, no, there's zx, there's x. There's no chain rule there. Zx is immediately a function of x. That's just zxx. Nothing to talk about there. Okay. And then, move some factors around and simplify. Weird coincidence in this case, those two terms happen to be the same, so you can combine them. And I've, of course, skipped over a little bit of algebra here, done representative parts of the calculation. Make sure that you can do the rest of this calculation. But this is the big idea. Things get a little different in this example. If instead of taking the partial with respect to second partial with respect to r, what if you were taking second partial with respect to theta? It's morally kind of equivalent. It just plays out a little bit differently. One thing you'll notice in particular is that this good fortune with the product rule. That convenient little thing doesn't happen when you're doing the theta second partial. So that's a great practice problem. Conveniently, I think it is a homework exercise, if I remember correctly. If it's not, I think it'd be a great exercise. I encourage you to do it. But in terms of strategy, in terms of how you append your diagram, it's the same basic thing. Okay. Alrighty, moving along. So I want to talk about the implicit function theorem. This is something that gets swept under the rug, unfortunately, in single variable calculus classes. And I suppose it's necessary in that context, because partial derivatives are going to come up a little bit here. Oh well. Anyway, very often a certain question gets asked in single variable calculus classes that is awkward, and I'd like to get rid of that awkwardness. So here it is. Sometimes a curve is given. It's described by an equation. And to the question of how would I compute the slope of the tangent line here, and how would I compute that? Very often it's just presented as, yeah, you just need to compute dy dx. Here's the, oh yeah, go ahead. Yeah, question.
How can you say, like, is it just like arbitrary that fxy equals 0 at that point?
Oh, I'm saying, let's suppose. I mean, very often, when you have a curve, curves are often described by equations. And remember, if you have an equation, one little slick move you can do is you can take whatever on the right-hand side, just subtract it over to the other, and you've got stuff equals 0. And it's a very common and convenient way to express an equation as, function equals a constant. In this case, 0, but whatever. Yeah. Okay. So here's what's wrong with this approach of, hey, I want to compute the slope of that. I guess I need to compute dy dx. The problem is, if you say dy dx, you are assuming that y is a function of x. And here's the thing. Look at this. It's not even close to a function of x. Right? It fails miserably, the vertical line test. Y is not a function of x. What are you talking about? Dy dx. You can't take derivatives of things that aren't functions. This is a big problem, right? So how to address this? Well, one way you can address this is say, look, all I really want to know is the slope of that tangent line, and that tangent line is entirely determined by what is the nature of the curve, what I'm going to call locally. Just nearby that point, I'm going to very happily throw away all the rest of this curve. I don't need any of the rest of that curve. Once I've thrown away the rest of that curve, now this function does not fail the vertical line test. This passes the vertical line test. Now I can view y as being a function of x. Right? Said differently, now I can view this as a graph, as opposed to previously I'd been viewing it as a level set. How can I tell the difference? Right? How can I tell under what circumstances? Here's the big question. Under what circumstances can I view y as a function of x? Now, note I've deliberately put in this little thing here. I don't care about viewing it globally, over the entire curve as a function of x. I just want to talk about locally, just near the point in question. Can I locally view y as a function of x? Given the equation for the curve and given a particular point. Okay, so again, this is usually completely swept under the rug in high school calculus classes. Even notice that in this context, this is what you might call a single variable example, right? This is the kind of stuff. Y'all did implicit differentiation all over the place in high school classes. Right? Okay, of this sort. Okay. So sometimes yes, sometimes no. This one's a yes. We've already talked about it. You just throw away the rest of the curve, passes the vertical line test, go about your business. This point, no. I don't care how much of this curve you erase. Right? You can erase all but the teeniest, tiniest little bit on each side of that point. If you leave enough on each side of that point to be able to talk about a tangent line, then you've left enough to create a problem with the vertical line test. So at that point, you can't even ask the question of what is dy dx. Because at that point, y is not even a function. You might as well be asking what's the derivative of a bicycle. Meaningless, garbage talk. Does not make any sense. Again, I'm not saying that the answer is, the derivative is undefined. I'm saying there is no such thing as a derivative. The question is garbage. Is everybody on board with this is, again, a kind of a nasty little problem. Okay. So, when can you do this and when can you not? Now, I'm not going to get real rigorous about this because this is not what Math 212 is. But I do want to point to what I think is kind of morally kind of the point, and that is, look, the reason that at a point like this you can't do it is because the curve kind of wraps under itself. It's the fact that at that point it is in the process of wrapping under itself that gives you this vertical line test problem. Right? Okay. All right, how do we tell when a curve is wrapping under itself? Well, it would have a vertical tangent line at that point. Now, it resists the urge to say dy dx is infinity. Resists the urge to say that the derivative is undefined. Again, I remind you, there is no such thing as the derivative at a function like I've drawn here. Okay? But we can say the curve has a vertical tangent line. There's no issue with that at all. Okay. How does this relate to something I can compute with? Well, here's the clever observation. At that point, having a vertical tangent line is synonymous with saying that the tangent vector is straight up, and the tangent vector is exactly what your velocity vector would be if you are moving along that curve right? And here's the thing, that curve is defined by f equals a constant, which means f is not changing. Right? So put this all together, and what this says is that as you are moving along the curve, and therefore the function isn't changing, you're moving vertically, you're moving directly in the y direction, and therefore the y partial of this capital F function is 0. That's the idea. Now again, there's some special cases and anomalies and points of regularity and rigor that I don't want to talk about in this context. Okay, so that's the big idea. And now I'm going to introduce you all to an idea of logic called the contrapositive. Y'all aware of the contrapositive? So just broad brushstroke, the contrapositive, if you have a statement P implies Q, then the contrapositive is the statement not Q implies not P. If you think about it, I mean, this, kind of think about a real world scenario, anyway, let's just think about it, just kind of walk through it. Suppose we know that P implies Q. Suppose we further know that Q is false. If Q is false, how could P possibly be true? P can't be true. If P is true, that would mean that Q is true, but we know it isn't. Right? So if Q is false, then I can conclude from that P is false. Right? So anyway, this is called the contrapositive. It's a nice little logical construction, and there's all sorts of fun and games to be had with, discussing how this relates to logic and set theory. We're not going to go anywhere near that in this class either. We're going to take this as a freebie. So that's how we. That's what we're going to apply here. Let me remind you. If we have a problem. If we have a problem such as that, we just argued that problem implies the y partial is 0. Right, that's this statement. The contrapositive of that statement is that if the y partial is not 0, then we don't have a problem. Everybody on board? Okay, so this is our big theorem. This is again, I'm not going to write the whole thing down, but this is the implicit function theorem. If you're interested, if you're looking at a level set, if you're looking at some sort of a curve described by an equation such as this, right, and you'd like to know, can I locally view one of the variables as a function of the other variable? Take the partial derivative, confirm you don't get 0, declare victory. That's the idea. Okay. By the way, it's really easy to keep. It's really easy to lose track of which variable is which. Notice here I want to view y as being a function. Whichever variable you want to view as being a function, that's the one you take the partial with respect to. Don't take the partial with respect to x. You're going to want to take the partial with respect to x. You're going to be thinking to yourself, but I want to know this x. I want to know dy dx. Don't I need the x derivative here? Isn't that what I'm here for? No. For the moment, we're trying to decide if we can view y as a function, and so go through the argument, and the punchline is you need to take the y partial to establish that. Okay. All right. So anyway, in an ideal world, all of that would have been discussed in a Calc 1 class when you first saw implicit differentiation. Of course, it's not really realistic in the sense that, well, we don't know partial derivatives at that time, so okay, we can't do it. But this does solidify something that was, I guess, necessarily swept under the rug in that context. Okay, but now we're going to go multivariable on this. What's the multivariable version? Multivariable version is highly analogous. Suppose you have, again, an equation, some function of, well, now 3 variables being 0, that gives us a surface. Right? And you could ask, reasonably, hey, what's on this surface, what's the partial in the x direction, what's the partial in the y direction? And you're thinking, what's that slope, or, what's that slope? Something like that. But again, before you go around taking derivatives, don't inadvertently take a derivative of a bicycle. You got to make sure the thing you want to take the derivative of actually is a function. So I need to know when can I view z as actually, in fact, being a function, and therefore something I can even talk about taking a derivative of. Okay. So analogous argument. This is what a problem would look like. Right? If I have a vertical tangent plane. If I have a vertical tangent plane, again, think about how, when you start throwing away most of this surface. Where's my little button? Oh, gosh. There it is. When you start throwing away most of this surface, and, let's say I preserve only that much of the surface, it is the fact of having a vertical tangent plane that will make this fail the vertical line test. Right? So again, you kind of go through the reasoning. If you have a problem, if you have an issue where at this point we simply cannot view z locally as a function, the problem means that the surface is in the process of wrapping under itself at that point, which means it has a vertical tangent plane. Which means that as you are moving in the z direction, right, as you're moving in the z direction, well, you're moving in that tangent plane. You're effectively moving along the surface where f is constant, and therefore that partial in the z direction is 0. Okay, again with the contrapositive, if problem implies the z partial is 0, then when the z partial is not 0, you have no problem. Yes, z is a function of x and y. Proceed. Take your derivatives however you'd like. Okay, so writing that down as a theorem right here. I do want to point one thing out. Again, whichever variable you want to view as a function, whichever one you want to view as a function, you have to take the partial with respect to that variable, confirm it's not 0 before you can declare victory. Okay, everybody on board? Okay, now, is it problem solved at this point? Well, there are some issues to be worked out. How do we actually take the derivative then? Right? The actual computation of the derivative. There are multiple variables running around here, and as I'm taking derivatives, what am I taking derivative with respect to, and how do I treat this other variable? It's easy to get lost in that. So I want to show you a strategy for this question, how to take derivatives. I've got the calculation written out in algebra right below what I have circled. I don't want to go to the algebra just yet. I want to scroll down past that for the moment. If you were following along in the lecture notes, just scroll down to the bottom of this next page and let's look at this diagram. So here's our scenario. We're looking at a level set. We're looking at some function that's a constant. That function, f, being a function of several other variables, x1 through xn, right? And my goal is to figure out in which case can I view one of these variables as being a function of the other. I'd like to, for example, be able to compute this partial derivative here, partial xi, partial xj. So before that makes sense, I have to ask the question, can I view xi as being a function of the other variables? Okay, so here's, again, ignoring the algebra, going back down to our diagram. I would like to view xi as a function of the other variables. And I'm just going to recopy them down here. It aesthetically, it feels weird to think of, in fact, let's ignore this this little arrow here. We'll come back to that. It's a little weird to think of this being a function of that. The arrows aren't supposed to go sideways, right? So I'm recopying all of these variables that xi is supposed to be a function of. I'm recopying them down here. Now our function arrows are going to move vertically. Okay, so here's the big trick, big strategy. The way we're going to actually compute the derivative we're interested in. Keep in mind what we are interested in is that. Partial of xi with respect to xj. That's what we want to know. How I'm going to get my hands on that is it's a tricky move. You always use the same trick. Somebody else figured this out. We're going to capitalize on that. The idea is to ask explicitly what is the partial of f with respect to xj, and capitalize on the fact that we already know the answer. Right? I know the partial of f with respect to xj. I'm on the curve. I'm on the surface. I know that f is not changing. So this derivative, partial of f with respect to xj, is 0. If the whole idea is I want to stay on that surface, right? But I also can compute that partial of f with respect to xj with a chain rule. So let's use the chain rule to compute that partial of f with respect to xj. Now, you might be thinking, oh my gosh, this is going to be brutal. Look at all the paths that we're going to have to deal with here. My gosh. So many paths. So many terms. What a nightmare. Right? Big trick. We're taking a partial with respect to xj. That means that I'm viewing all of these other variables down here as being constants. Right? Viewing this f as a function of these variables, taking a partial with respect to that one, all the rest of them are constants. Okay, so good news. That means that, whoops, I hit the wrong color. Whoopsie. That means that all of that's constant. All of this stuff in here is constant. All of this stuff over there is constant. I'm taking a partial derivative. So there's not millions of terms. There's 2 terms. Right? And here they are. There's that term. And there's that term. And let's look up here at this equation. Let's see how they fit in. So that sort of dark green, light green path, right, makes that term. And then the orange, yellow path, there's the yellow factor. What happened to the orange? How come I didn't put the orange in here? I claim that this orange derivative is 1 because it's the partial of xj with respect to xj. And that's pretty clearly 1. Everybody on board? So a lot going on here. But this is, I think, a pretty good way to lay out what's going on. We've got this function that's, in fact, constant. Right? It's viewed as a function of all these variables, but I want to view one of them as a function of the others while f is being held constant. That gives rise to this picture. The partial derivative I'm interested in means that most of these things are constant, and then I just write down the chain rule. This right here is the chain rule as it applies to this diagram. Okay. All right. Now, with all of that done, then it's like I say, it's all over but the shouting. This is what we wanted to know, right? I want to know the partial of xi with respect to xj. So solve for it. And a little bit of algebra, and there you go. All right, now, do you have to make this diagram every time? Do you have to go through this whole song and dance? No, conveniently, this is a general argument. So we effectively just kind of proved a theorem, sort of, here. So you are welcome to just cite this result. Right, I'm going to get rid of all this stuff now. You're welcome to just cite this formula. Be careful, though. Do notice that there is this minus sign here. Gosh, that's important. It's kind of counterintuitive. Again, you got to resist this temptation. A lot of students who take a symbolic manipulation approach to this business will say, "Oh, those cancel, and shouldn't it just be no minus sign?" Super tempting, and super wrong, crazy wrong, completely bypassing all actual valid arguments about this question, right? And furthermore, making grossly inappropriate assumptions about what's actually going on. Right? So don't don't do that. Make double, triple, extra sure that you put this minus sign in there. Just strategically, real quick strategic point from a grading point of view. If you write down this formula, hey, cool, that's valid, true formula. Do the calculation, full credit. Everybody's happy, right? If you forget the minus sign, what you wrote is not only not true, but it's highly suggestive that you don't understand anything about what's going on. Certainly, the student who has absolutely no understanding of how this works, that student would write down this formula without the minus sign also. And if you can't distinguish yourself from someone who, in fact, grossly does not understand, I can't give the points, right? So, like I say, it's crazy important. Please, please, please do not forget that minus sign. Is everybody on board? Everybody understand why this is a big deal? Yeah. Okay. By the way, now let me give you sort of a real quick argument. The reason I drew this way in the first place, kind of a back of the envelope point of view on this, is that if you ask, what is the partial of f with respect to xj, and if you, in shorthand, realize that you're viewing xi as a function of xj, then you can just kind of shorthand the diagram like this and say, look, as xj changes, one thing that's going to happen is that xi is going to change, and those changes will propagate up to f. The other thing that will happen as xj changes is that xj changes will directly affect f. Right? So changes in xj affect f in two different ways. One is by way of xi, the other is directly. And this gives rise to this exact same formula up here that we were just looking at. Same formula which gives rise to the same result. So I don't like to start with it from this point of view because I do think that leaves a lot of important details out. But once you understand those details, this is a nice summary. Alrighty, quick example, and largely this is just for procedural necessity. Suppose you face a question like this on an exam, midterm exam, final exam, whatever. Okay, in the way that this question was phrased, I was being explicitly, I was kind of generous, really, explicitly noting that I first have to ask if x could be viewed as a function before I ask you to compute a derivative of it. Right? Note that this will not always be the case. Right? In fact, in sort of, let's call it real life, right? When you're out and elsewhere on this campus, engineering classes or whatever, and they are interested in computing, in an example like this, what is the partial of x with respect to z? They're probably not going to say, and by the way, don't forget you're supposed to remember that to actually check to make sure this is a function before you start going around and taking derivatives of it. Right? They aren't going to do that. Right? In practice, day in and day out, what you will see is this line is simply not here. You'll see stuff like this. Here's an equation. What's the partial of x with respect to z? Okay. And it's your job to make sure that you remember that, that question's getting ahead of itself. It's asking me to take a derivative of something it's not even clear that this thing is a function. And in order to avoid the preposterous problem of inadvertently taking a derivative of a bicycle, I have to first establish that x is actually a function. Right? So, again, I hinted at it real hard here. That will not always be the case on exams. It remains that you do have to check that. Right? Otherwise, again, you're just making tremendous assumptions that might end up being false. Okay. All right. So, So, step one. How do I address? Can I view x as a function near that explicit point? Well, here's how you go about doing that. Partial with respect to x. Again, the variable that you want to view as being a function. That's what you take the partial with respect to. Right? I want to know about this particular point, 1, 2, 3. Plug in that particular point. The value of this partial derivative becomes 4. And because that is not 0, yes, I can view x as a function of z. That's the first half of the problem. By the way, when I grade these, this is about half of the points. I'm telling you right here. Right? That's about half of the points. All right. Now, having established that x is a function, given that this is a function, it is perfectly reasonable to ask what's the partial derivative of it, let's say with respect to z, and applying the formula from the previous page, which shows up, like this in this case. Then it's just a couple of calculations, and these partials are easy. Let's see. I got to zoom out one. This thing, right? Its partials with respect to z and x. By the way, conveniently, we already computed that x partial. That's convenient. Right? But the z partial, easy to compute. Right? Again, huge point. Don't forget this minus sign. If you forget the minus sign, it looks like you have your work is indistinguishable from someone who has no earthly clue of what's going on here. And again, you can't have that, right? So please don't forget that minus sign. And then it's all arithmetic at this point. You plug in the given point, and there's your answer. Okay. All right. Here we go. Next topic. Moving on to directional derivatives. So this is kind of an interesting conversation. It's a twist on something we've already done before. So just a reminder, these formulas right here, one of the big interpretations we took from the chain rule is that the Jacobian matrix can be viewed as that which you multiply by an input velocity to get an output velocity. Right? This is one of our geometric sort of interpretations of the. You can view the Jacobian matrix as a bookkeeping tool algebraically. I like to think of it as a relationship between input vectors and output vectors, such as velocity vectors. Okay. By the way, it works just as well if you will, multiply by dt on both sides, victimless crime, and think of it as an approximation of how much the function changes when you change the input by a certain amount. So again, the Jacobian is a relationship between input vectors and output vectors. Okay, old news. Here's the special case we want to consider, though. If f is a real valued function, by the way, real valued just means that the output values are real numbers. not vectors, right? So just, scalar valued function. Then this matrix, if you go back and look at the formula for it, it'll have only one row. Right? There's only one output variable to take partials of. Thus, you only get one row. So this formula then, in this case, as it turns out, can be rewritten. Right? This calculation here is algebraically identical to that. Right? I mean, it just happens to be that the process of multiplying a row matrix times a vector, right? Row times column vector is it's computed as a dot product of this row with that column. It's a dot product. And furthermore, this thing viewed as a vector is something we've already talked about. It's the gradient. Again, it was just kind of a notational shorthand convenience as we talked about it before. Okay, so this, again, this only works in the real valued case. And anyway, but it's a nice little change. I get to rewrite a matrix multiplication as a vector dot product. And it turns out there's tremendous value in this being, even though it's arithmetically, it's, the computation is identical, viewing it as a dot product is going to be valuable because we have geometric knowledge about the dot product. That's going to help us do good things, yeah.
What do you mean by a real value case? Does that mean that if
real valued means that the function has R1 or a subset of R1 as its target. So valued means I'm telling you about the values of the function or what comes out of the function, and I need those to be just real numbers. Yeah. Okay. Yeah, so this gives us a kind of a geometric interpretation of the gradient. The gradient is a vector in the domain with a curious property that if you dot it with your input velocity, then what it tells you is your output velocity. And there's a vector in the domain that does this, that dots with velocity vectors in the domain to give you velocities in the target. Okay, anyway, this is more of a reminder than anything else. Okay, so now the book makes from this a definition. Here's the book's definition. We're, of course, this being, I'll just say, anyway, we're going to go with the book's definition on this. I'll come back and put an asterisk on this in a moment. But here's the definition of this thing called a directional derivative of a function. Directional derivative of a function at a point says, compute this expression. Dot product with the gradient, just like we have on the previous page. Keep in mind, our discussion on the previous page is that this formula computes output change. Right? So the reason we're interested in this thing in the first place is because it's an output change. So this thing that we're calling the directional derivative is telling you about how the function is changing. Either as a rate of change, if you've dotted with a velocity vector, or as a differential change, if you've dotted it with a differential in the input. Okay, here's the little asterisk. Per the book's definition, and this is not the only book that makes this choice, this vector u has to be a unit vector. And let me go to bat for the book here and explain, part of the motivation for that. Look at the term directional derivative. How do we describe directions? And it's tempting to say with vectors, but I'll point out that, a vector is a direction and a magnitude, right? Vector is a direction and a magnitude. If you want to isolate just the direction, but kind of a pretty reasonable way to do that would be, let's forget about the whole magnitude part. I just want to talk about just the direction, and a unit vector, using a unit vector that points in a given direction, arguably in some sense is the best way of ignoring the magnitude. So, it's not the most implausible idea in the world. Okay, now that I've gone to bat for the book, let me make a yeah but case. case for the other side. There are books that don't make this choice. This is a cultural discussion at this point. Don't as far as Math 212 is concerned, don't worry about the following. But culturally, just so you'll know, a lot of books don't do this. A lot of mathematicians don't see the point of restricting the term directional derivative just in the case where the input velocity is a unit vector. Because look, this thing is always true. This formula here is true no matter what input velocity you have. And how fast the function is changing is always interesting. So why would we restrict for semantical reasons? This seems like a bad choice from this other point of view. Right. So anyway, the reason I'm telling you this is you guys have to be aware when you're out in the real world and the term directional derivative comes up. Uh-oh, wait a minute. This person who just said directional derivative, which textbook did they learn out of? Do they interpret, are they suggesting that I interpret my input velocity only as a unit vector, or might they be taking the broader interpretation of the term? It is not clear, right? You might even ask them to clarify. Excuse me, when you say directional derivative, how do you define that? Right? Because it can matter. Okay, I wish I had more time to talk about that, but I don't. So as far as Math 212 is concerned, this is part of the deal. This input velocity has to be a unit vector if you're going to use the term directional derivative. Okay. All right, so a couple different ways to think about this. One is, notice that it is, of course, as kind of we just discussed, it's just a special case of the chain rule. We wrote the chain rule. Here's the chain rule again. This is how you write the chain rule for a real valued function. This is just the special case of, hey, what happens when you have a unit vector? So that's a pretty reasonable way to think about directional derivatives. Think chain rule. And yes, furthermore, that input velocity is a unit vector. Okay. I also like to point out that it's sort of the opposite of a special case. It's a generalization of the partial derivative. Or said differently, a partial derivative is a special case of a directional derivative. Because let's consider what happens when your unit vector is a standard basis vector. Not just a unit vector, but even more special, explicitly a standard basis vector. Well, this dot product, keep in mind the gradient is made up of a bunch of partial derivatives. If you take a vector of partial derivatives and dot with a vector that's all zeros, except for a single one in one position, then whichever position that one is in, you'll get the corresponding partial derivative. Right? So in that special case, a directional derivative is exactly a partial derivative. And this is nice because y'all already have a pretty good sense of, what's a partial derivative? Well, it's slope of the graph. It's, Dfds in that direction. It's, if you move a little bit that way, how far does the output move that way? So you can see that the directional derivative is really just kind of that same thing. It's just like a partial derivative, except more general in the sense that it's allowed to point in any direction. Okay. All right. One last little observation I'll make before we go on. I want to explicitly show you that you can interpret directional derivatives as DFDS. Let me remind you why we would care about this. If you've got, some function, real valued function of position, you might be interested in how that function is changing independent of the experience of a specific observer. So for example, maybe I'm here and I want to know how the function's changing as I move that way. Just kind of generally, is the function changing a lot as I move that way, or is it maybe not so much? I don't really care that Bob personally is moving fast. That's going to mess up my information. I'm thinking about a lot of people who might be moving in that direction, but maybe a little faster, a little slower, what have you. I don't care about Bob's personal experience. I want to know about the function itself. in the per unit distance traveled, not per unit time. Per unit time brings in, again, well, how fast is he? If he's in a jet airplane moving really fast in that direction, then yes, f is changing really fast. It's not what I want to know. Okay. So, very reasonable thing to want to compute, and the directional derivative computes it. And here's an argument as to why, and I'm out of time, so I can't give you that argument now. We will pick up here on Wednesday. See y'all later. Have a good day.